And I'd like to welcome you to today's webinar, Intro to Site Investigation with Danny Deloy from Mott MacDonald. However, before getting into Danny's presentation, I have a few announcements to go through. So first of all, just a little bit about us. So TAC-YM as a group was created in 2014 as a platform for communication between students, young professionals, and mentors within the industry and other member nations. And as a group, we've been actively creating opportunities for young professionals and students to participate in regional technical talks, regional and international webinar series, field trips and site visits, and conferences and workshops. And so there are 4 active groups for the young members located in Vancouver, Toronto, Montreal, and Kingston. TAC-YM also actively advocates for students, and TAC as a whole has 2 scholarships that are geared towards the student population. The undergraduate scholarship is valued at $2,000 Canadian and is intended for undergraduate engineers in the fields of geological or civil engineering. And the Dan Eisenstein Memorial Scholarship is valued at $6,000 Canadian and is intended for postgraduate students planning to undertake or currently undertaking postgraduate studies in the field of tunneling at a recognized Canadian university. So the applications for 2023 are available, and the deadline to apply is May 19th. So if you are a student, if you know a student at the undergraduate or graduate level, please encourage them to apply. The applications can be found on the Tunneling Association of Canada website at tunnelcanada.ca. Another announcement that TAC-YM has is we are adding 3 new steering committee sub-chairs. And so we would like to welcome Emily, who is going to be taking on the role of sub-chair communications, Lauren as the sub-chair for academic and university outreach, and Graham as the sub-chair for industry outreach. And so if you are looking to get involved or would like to get involved with the Tunneling Association of Canada Young Members Group, there are opportunities to join that are available, especially as we are looking for volunteers to join our subcommittees for industry outreach and academic and university outreach. So reach out to us on social media at Tunnel Canada on Facebook, at TAC_young_members on Instagram, or send us an email. So that's tac-ym@tunnelcanada.ca. If you are not yet a member of the Tunneling Association of Canada, you can find the application to be a member online at tunnelcanada.ca. And then just as another announcement, so we have a save the date for next month's Tunneling 101 webinar, which will be presented by Josephine Morgenroth, and that is titled Machine Learning and Tunneling, Not If, But When. So that will be on April 20th. 12 p.m. Pacific Standard Time and 3 p.m. Eastern Time. So watch your email for details and watch online on social media for those details. Now, to the main event. So today I'd like to introduce Danny Deloy, and Danny is a principal engineer and project manager with Mott MacDonald, managing and leading the design and projects varying in complexity, from small trenchless jobs to large-scale tunnel projects. Her technical expertise ranges from planning and leading fieldwork assignments through technical design and coordination to tunnel condition surveys and inspections. She has worked on a broad range of tunneling and trenchless projects, from pre-feasibility to detailed design phases through to construction oversight. And if that didn't keep Danny busy enough, Danny is also a leader on the TAC EDI task force, and it was TAC's 2022 Young Member of the Year Award recipient. And so, Danny, I will give the floor over to you.
Thanks so much, Tim. And I am assuming everyone can see my screen now, and that we're good to go. Yes?
Just about.
All right, so while we're waiting for things to get set up, I encourage everyone to bring out your smartphones. This is going to be a slightly interactive presentation, so have them ready because I'm going to be asking some questions during the presentation, and you should be able to use your phones to respond. All right. So I'm going to assume we're good to get going. All right, so thanks everyone so much for having me. I'm excited to talk to you today about geological and geotechnical site investigation and characterization. All right, let's move this forward. So I just want to start by doing a quick EDI moment. As Tim mentioned, I'm the lead for the TAC EDI task force, and one of the initiatives we're rolling out is EDI moments. So this is like a safety moment, but we talk about an EDI topic. And the topic today is, what is an ally? So an ally is someone who supports and unites themselves with another individual or group to promote a common interest where both benefit. Relating to diversity and inclusion, an ally is someone who actively and consistently seeks to end the systemic disempowerment of people belonging to a group. Allies can help improve feelings of inclusion and belonging. So how do you practice allyship? Be a true listener, respect people's lived experiences when they share them with you, provide solidarity, stand behind, not in front of, provide the support you are asked to provide, not what you would imagine what would be helpful or what you would do. Apologize for any mistakes you make. For example, if you use incorrect pronouns for someone or incorrect pronunciation, and move on without waiting for forgiveness from that person. And recognize the groups that you wish to ally with are not homogeneous in their thinking. So now on to the agenda about what we'll be talking about today. So we're going to go through what's the purpose of site investigations, the geotechnical parameters that have been our interest on tunneling projects, some different methods about data collection, but we're not going to go into exhaustive detail on that, field and laboratory testing, staging site investigation programs, and then we'll talk a little bit about uncertainty in parameters and interpretation, and finally, we'll end with some data visualization. So I want to start though by saying, giving you a little bit of a disclaimer, and that is that every single tunneling project is unique and that there is absolutely no one-fits-all solution. So the answer to site investigation and the questions in this presentation are typically, it depends. So let's start by thinking about, why do we need site investigation information? And the site investigation information really comes down to defining risk, selecting methods of mitigating that risk, and allocating that risk. We use site investigation information in tunneling to select our alignment, whether that be in horizontal or in the vertical plane. Selecting the right construction methods, so that can be both excavation methods, dewatering requirements. Are you building in hard rock and doing drill and blast? Are you building a soft ground tunnel? Do you need face support? To inform our design, so what sort of ground stabilization do we need? Are rock bolts sufficient? Do we need a bunch of shotcrete? And then also for evaluating cost and schedule. So how quickly can we build a tunnel? How much is it going to cost? What are the risks associated with that as well? So I'd like to step back, and I'm sure some of you have heard this quote before from Donald Rumsfeld, but there are known knowns. So those are things we know that we know. There are known unknowns. So those are things that we know that we don't know. And then there are also unknown unknowns, things we don't know that we don't know. So let's take a moment and think about how this applies to tunneling. So now is the time where I want you to get out your smartphones and scan this QR code here, so you can log on to, or you can log on to menti.com through a window in your browser and enter this code below. And once you've logged onto your phone, you should be able to give me a thumbs up so I know that it's working for you. So give me a thumbs up once you've scanned that QR code and are on Menti. Awesome. Okay, I'm seeing a couple thumbs, so I'm going to move on to the first slide here. And I would like you to give me an example of a known known as it would apply to a tunneling project or a site investigation program. So what is something we know that we know? This is something that you, at the start of a project, would have a lot of certainty about. See if we get any examples up here. The alignment. Awesome. So the alignment would be a known known. We know exactly where the tunnel is going. It's something we've selected. It's something we have a lot of certainty about. What is something else? The tunnel dimension. Yeah, we might know the tunnel dimension. Engineering. So engineering is pretty broad. I would say that engineering isn't really a known known. whether it's a rock or soil tunnel. So we might have some certainty on the geotech conditions. All right, so let's move on to the next thing here. And what's an example of a known unknown? So this is something we know that we don't know, or we know that we don't have a bunch of certainty about at the start of our project. So fill in those answers and we'll wait for it to pop up on the screen. Soil parameters, exactly. So that's something we know we don't know without doing site investigation. The length of the tunnel may be a known unknown. That might adapt over as the project is going. We'll wait for a few more answers here. The geology, definitely the geology. We might know a little bit about it, but we don't know a lot until we do a site investigation program. Groundwater conditions, that's another definitely known unknown that we would want to get more information on. Rock distribution, perfect. RQD, great. So those are all things that we can get more certainty about by doing a site investigation program, but at the beginning of the project are definitely a known unknown. We don't have much information about it at all. So the last bit that we think about when we're talking about a site investigation program are the unknown unknowns. So these are the big risk items. So what would be an example of an unknown unknown on a tunnel project? Something that you don't know that you don't know about. We'll wait for a few examples here. An anomaly, buried objects. Yeah, buried objects are a key one there. Hidden tiebacks. So man-made things that you don't know are there. Maybe you have poor construction records in the area and you encounter them and then they cause a lot of challenges in your project because you didn't expect them to be there. Historic workings, yeah, unexpected shear zones. That's another great example. So faults or shear zones that you didn't have any evidence of, didn't occur during your site investigation, and you don't know that they're there. An old fill area. So those are all great examples of unknown unknowns, unmapped features. So just wanted one example here, and just the impact it can cause when you have arguably an unknown unknown or a known unknown, giving the example of the Alaska Way Viaduct project. So many of you know that there was a huge delay on this project. They had to build a rescue shaft, design a crane, remove the TBM cutter head, and replace the main bearing of the tunnel boring machine. Now, there was a lot of litigation back and forth over to what the cause of this was, but one of the claims said it was due to a fragment of a steel pipe that was encountered by the tunnel boring machine in late 2013. Now, there was questions back and forth as to whether this pipe should have been a known, whether it was in the documentation or if it was an unknown and it was something that was completely unexpected. Now, I'm not going to go into a lot of detail on this case study, but you can imagine the price tag that comes with this and why having certainty in whatever you can during your investigation is key to the success of your project. So let's talk a little bit more detail about what information do we need. One of the things that came up through those known unknowns and unknown unknowns were the subsurface conditions. So this is a key for your tunneling projects to classify the subsurface conditions and characterize them. So this looks like the distribution of rock and soil, the different types, their properties, the condition of them, and stratigraphy. Another thing that was highlighted in those unknown unknowns was obstructions. So we want to get a good idea of past construction in the area, of boulders we may encounter, of groundwater conditions, and other potential risks like environmental conditions, previous use of the site if there was a tannery there that might have caused some contamination. And we want to get a really good handle on all the different sorts of geotechnical parameters we need for tunnel design. So there's parameters we want to get for soil, for rock mass, for other sorts of conditions, groundwater, and environmental. And we'll talk about some of these in a little bit more detail. So let's first talk about rock mass conditions, about the strength and quality of our rock mass. So why is this something we care about in tunneling? Well, it's an input into the assessment of our rock mass behavior, and it informs our construction methods and support selection. And we get this information by field mapping, by core logging, through laboratory testing, things like unconfined strength testing, and in situ testing as well. So why does this really matter? Let's look at it in some photos. the variability of our rock mass conditions can completely impact the behavior of our tunnel. So this is an example of a TBM tunnel where excavation and initial support was in good ground conditions, and you can see a nice beautiful profile there. That's all exposed rock, so really nice tunneling conditions. Now, same tunnel, different rock mass conditions. So now we're into fair ground conditions, and you can see how the support has had to change there. So now we have bolts and mesh and a lot more raveling of the rock mass or spalling on the sidewalls. Now we're into poor conditions again on the same tunneling project, a lot more support there, a lot more time, a lot more cost to install that support. And same tunnel again in our extensive overbreak and stoppages caused by very poor ground conditions. And these conditions weren't expected during the excavation, so weren't designed for and caused some significant delays on the project. So that's why this is just one case example of why understanding those rock mass conditions are key at the outset of our project. So another thing that we'd want to know is the soil type and index parameters. And one of the key reasons to know this is the clogging potential of the tunnel boring machine. That's something we can get with Atterberg limits. So there's different ways we collect different pieces of information that are key for our tunneling design. So grain size distribution is another key soil parameter for building a tunnel in soil because it informs our TBM type selection, and we get this information through lab testing through sieve tests. Presence of cobbles and boulders. Again, this is another important thing to understand and to get through our site investigation if we think it's going to be a risk, because cobbles and boulders can cause significant delays to projects and also inform our construction method selection. Now, getting information on cobbles and boulders can sometimes prove to be a challenge. Sometimes it's hard to get information on them through boreholes, so often we use geophysics or test pits or past project experience to get information and distributions and strengths of cobbles and boulders. For tunnel design, abrasivity is another key parameter as it impacts our rate of tool wear. And in turn, our advance rate prediction. So we can get this information from lab testing and petrographic analysis of rock and soils. Another key parameter is in situ stress. So in situ stress can have a huge impact on ground behavior. It can cause squeezing, spalling, overstressing, rock bursting in extreme cases. And we need to know those things in advance to inform the selection of the construction method and the support we need. And often in situ stress testing is challenging, but it is possible. But we also rely on past project experience in similar ground conditions in similar areas to get information on in situ stress. So this is just an example on the right here of failure that was exacerbated by in situ stress. Mineralogy is another key thing that we look for during our site investigation program. So different types of minerals can be detrimental to excavation. This could be swelling minerals or silica dust. On the right, you have an example of a project where swelling minerals caused about 2 meters of floor heave in the tunnel. So you can see how significant an impact that can have. And we get information on the mineralogy through petrographic analysis and X-ray diffraction. Groundwater is another key thing that we want to look at. So why do we care about groundwater? Well, those are some photos of groundwater inflows in tunnel projects on the right there. And significant inflows, as you can imagine, can have huge project delays, and they're really hard to deal with after you've already excavated. It's easier to deal with them ahead of time. And just for context, that photo on the right, that thing that looks like a rope, that's actually a stream of water coming from a 2-inch borehole. So really, really high pressure safety issue at that point. So we want to know those groundwater conditions ahead of time. And we do that through in situ testing, through monitoring wells and piezometers, and through forward probing during excavation as well, and can manage it through pre-excavation grouting. So let's now talk about the stages of a site investigation program. Typically, we don't do all the investigation at once. There's different stages of investigation aligned with the progression of our design. So at the concept or feasibility stage of a project, there might be limited on-site site investigation. We'd start with a desktop study. Then as we move into preliminary design, moving into field mapping and a site walkover in order to inform and plan your stage 1 investigation program. And then as you move into detailed design, often you'd plan a stage 2 investigation program where you're filling in more details. The deliverables out of each of those look slightly different. So at the desk study stage, we'd be looking at something like an initial geotech assessment, moving into a preliminary geotechnical data report, an interpretive report during your stage 1 investigation. And as you get to the end of your detailed design, often your deliverables look like a final geotechnical data report, interpretive report, and geotechnical baseline report. Now, I'm not going to talk in a lot of detail about those different deliverables today because we're going to talk more about the investigations themselves. So a desktop is typically what you do at the start, at the concept stage. You should always be starting with a desktop study, looking at historical investigations and available data that you have from past projects in the area, any past project construction experience, available geological maps, be it bedrock or surficial or soil data, air photos of the area, especially if you can get air photos of the area over time to see historic use and change in the landscape, information about seismic hazards or other hazards. Walking through the area on Google Earth can be really useful, looking for overhead obstructions, roads, railways, those sorts of things, and any areas of interest, be it archaeological areas, if there's areas of environmental sensitivity, and understanding historic use of the site, which can help you understand if there's any contamination. The next stage we would move into is field mapping and a site walkover. So now we're assuming we know that where our project area is, where our approximate tunnel alignment is, and we want to get a better understanding of potentially adjacent infrastructure, sensitive buildings or overhead power lines, if there's any access constraints that we might be dealing with both during our site investigation, but also during construction. We'd be looking for evidence of potential geohazards, so that's things like slope stability issues, completing geological mapping of outcrops or subcrops if there is exposure in the area, collecting information on jointing and rock mass conditions, and geology, and also selecting locations for further investigation. So a site walkover is the best way to site where you want to actually be drilling your boreholes or performing any other types of investigation works. Remote sensing is another way we collect data. So methods of remote sensing include LiDAR, photogrammetry, collecting drone footage or satellite data like INSAR, and that can be done, those different methods can be done airborne. There's mobile terrestrial ways to collect that data, so that means on the back of a car, or static terrestrial, so on a tripod. So the examples on the right are just different types of LiDAR data. And through that, you can get topography, a very good model of your site surface. You can do site characterization and also gain geotechnical data. So from LiDAR surveys, for example, you can get joint orientations, shear zones, those sorts of things. Next, we get into our actual intrusive site investigation methods. So test pits and trenches. These involve excavating the first few meters of soils, and those help you understand the stratigraphy that you're dealing with. You can identify cobbles and boulders in the distribution using these type of methods. But the challenge with test pits and trenches is they're limited in depth and stability depending on the soil types, and you only can collect disturbed samples from test pits. Next, we have geophysical surveys. There's a variety of methods available for geophysical surveys, and I'm not going to get into detail on all the different methods today, but those can help collect different types of subsurface information. And then boreholes, where you're collecting samples of soil or rock and can complete in situ testing. So everyone grab out your smartphones. We have another activity here. that I'm going to ask everyone. So, should you do geophysics or boreholes first? I'd like to see your votes on which you think you should be doing first. There's 4 answers to pick from: geophysics, boreholes, it depends, or not sure. So I'm going to give a minute or two for folks to respond here. So far, I see 2 votes for boreholes, 1 for it depends. Oh, it depends is taking the lead. You say geophysics, more saying it depends. I'll let the answers keep rolling in, but my opinion on this topic is just like everything with it in geotech, is it depends. The most important thing is that you're tying your geophysics and your boreholes together. Sometimes you do geophysics first and you'll find anomalies that you want to check by using boreholes. Sometimes you'll do boreholes, and in order to tie your boreholes together, you want to do geophysics. So I don't think there's a right or a wrong answer about which you do first. I think the answer is it depends, and it's on a case-by-case basis. All right, so we have another activity here. So I'm going to give some background. So this is a project where we have each color there shown on this section is a different geological unit. These are all rock units, and they're all dipping to the left-hand side of the page. So those dashed lines there are the contacts between the different units. If you look at the plan in the top, you'll see blue areas, and those blue areas are glaciers. So if you're drilling on top of the glacier, you do need to consider that you're going to be building a platform on ice and dealing with a moving glacier. On the glacier to the left-hand side, you can see a red squiggly line. You can see it in the section as well. That's an inferred fault. So no evidence of that fault, but it's assumed to occur there due to the contact between the 2 different units. So what I would like to know, if you only had the ability to do 1 borehole, where would you locate that borehole? I'm seeing a couple different locations that people are picking, so we'll give a few more seconds here. Someone's picking the top of the mountain, I see. So just for scale too, the tunnel is under about 1,000 meters of cover. So drilling from the top there, we'd be drilling down about over 1,000 meter borehole. Do you have any other thoughts? I see 3 dots on the page so far. Some at the end, some at the portals, some on the purple. Awesome. So lots of different ideas of where we should be drilling boreholes for this alignment. And I'd say there's a balance to be considered here. Again, the answer is probably it depends. Depends on which of these rock units are more challenging to go through, which we want to get the most information on. But I would avoid drilling on top of the ice. I'd say drilling on top of a glacier is extremely challenging, and we'd likely be unable to drill a hole on top of the glacier. I like the one that's located on top of the purple over here on the left-hand side, because you could do an angled borehole there and get through quite a few of the different units to characterize them. The one over here on the side where the portal is too, you could do an angled hole there to get quite a bit of information. But you definitely want to be characterizing that fault too, because that's a high risk area. So maybe you could set up on that purple location and drill 1 to the south, or to the right, sorry, to intersect quite a few units, and 1 across the fault. Because when we think about tunneling and planning site investigation programs, one of the key things we want to do is target the areas that are highest risk to the tunnel project. So if we think of this whole alignment, and I gave you very little information on these different rock units, But if all those green and yellow units are fairly similar and it's just a little nuance in the different conditions, whereas that fault has the risk to stop the project for a significant amount of time, knowing where that fault is and the conditions of that fault might be more important than getting lots of information around the rock units around the rest of the alignment. So one thing when we're doing our site investigation programs is that we want to characterize varying site conditions. We've got to recognize that tunnels are linear projects that go through a range of conditions, and that rock mass variability, even if we're in the same unit for the entire length of the tunnel, can lead to different performance of our tunnel. For example, the angle of schistosity can cause a significantly different response to our tunnel. So this is an example of a project that was all constructed in the same schist unit, but the angle of schistosity relative to the tunnel or to the loading direction significantly changed the compressive strength of the rock mass. So what does that manifest to you in the tunnel itself? So these are two examples of the same tunnel with different angles of schistosity, and you see a face here that's pretty much completely collapsed versus a near vertical face here. So very, very different responses in the tunnel in the same unit. And this is the same sort of thing where we have same tunnel using the same support system throughout the tunnel, and with the variability in the ground conditions, we get everything from good performance to 1 meter of floor heave to a completely excessive amount of heave where the tunnel has become completely unusable or unpassable. We also want to understand the variability that comes from testing. So this is an example of 4 different labs. So you have lab 1, 2, 3, and 4 shown by the different colors there, and all on the same rock unit. So the results you got were fairly different, or a different range in unconfined compressive strength versus crack initiation strength. So which lab do you rely on? Which testing results are correct, or do you span all of them? And that has to be an informed decision by the engineering team, deciding what is appropriate. So is that true variability in the rock mass, or is that just variability coming from the quality of the testing? And then one question that I'm sure everyone has been faced with before is how much investigation is enough? Now it really comes down to there being lots of guidelines, but the answer is it depends. Uh, the more challenging your geology is, the more complex it is, typically the more investigation you want to do. If you have simple geology, you can do less. It also depends on where your tunnel is located. If it's more challenging to access your tunnel location, if it's in the remote area where we were looking at that last tunnel, where you have 1,000 meters of cover and you're dealing with glaciers, you might be getting a lot less site investigation information than if you're dealing with an urban environment that has easy access. You're going to want to target key areas of your tunnel as well, such as your shafts and portals and any special problem areas if you have known faults and that sort of thing. So I pose this question to you. This is an example of a project. The colored lines you see there are boreholes. The green represents soil. The yellow represents weathered rock. The orange is rock. Where you see white, that means that the core was lost during drilling. And the pink line over here on the left-hand side of the screen is a geophysical survey that you did, and that line is interpreted to represent the contact between the soil and the weathered rock. So the question, oh, sorry, and this black line here, that's your tunnel profile. So the question for you is, do you need more investigation? Why or why not? We'll give a few minutes here for folks to answer. I'm going to switch back to the screen over here just so you can see. the profile one more time. So do you need more investigation? Why or why not? Yes, possibly Hidden Valley. Another yes, potentially Buried Valley. If there's budget, then yes. Yeah, I like that answer. Yes, to find out the dip in the geophysics. Yes, yes, water level, soil profile varying. Yes, no, yes. So lots of different thoughts here. Yes, investigate the dip in the purple line. So I would say the answer, in my opinion, again, is that it depends. It depends on what your design solution is. Does your design solution care that you're going through rock or soil, or do you have a robust solution that is sufficient no matter the ground conditions? If the soil or a dip in that soil presents a big risk, then it would be more important to characterize if that actually exists or not. Um, do you have enough fair information or not? It all comes down to risk mitigation. Might be a fault. So if you do think there's a reason that there's a fault there, that might be something you want to investigate more. So again, answer is it depends. And like I said, it really comes down to risk versus mitigation. And there have been multiple studies done on the comparison of the amount of site investigation you do versus the cost of failure during construction. And usually there's some sort of sweet spot in the middle. And what that sweet spot is varies from project to project. And there's always debate over whether you need to do more investigation or not. But it's been proven that the more investigation you do, the lower the risk of failure during construction. And this is just a plot here on the left of changes requested as a percent of the engineer's estimate versus the total length of borehole drilled. So as you can see here as well, as the length of borehole drilled goes up, the cost of requested changes comes down. And there's different industry guidelines as to where that amount should be. And often it's in this like 0.7 to 1.5 guideline, but you can see most projects do less than that. So another activity here for you. So this is an example of a geological profile that was developed from a phase 1 investigation, but unfortunately no testing data or borehole logs are available. You can see a little bit of geotech information here. You're going below a river. The gray is your TBM alignment. So you have a TBM retrieval shaft and a launch shaft. You have a tunnel alignment here, which is about 1,200 meters long. It's at about a depth of 40 meters. You're going through clays. Your shafts are excavated through silts and sands, and there's no glacial deposits shown on this alignment. Now, these are imaginary numbers, but go with me. You have a budget of $200,000 for your phase 2 site investigation program, and I'd like to know how you would allocate your budget. Assuming boreholes cost 1,000 meters per meter on land, $3,000 per meter in the river. Geophysics costs $5,000 per 100 meters on land, $10,000 per 100 meters in the river. And your testing program costs are here. So you can do a grain size test for $100, Atterberg test for $100, abrasivity tests for $500, and you can also install piezometers for $5,000 each. That includes the drilling for that piezometer, but not collecting any geotech information from that. So I'll give you a second to digest that. And I'd like to know how you would allocate that $200,000 for your phase 2 investigation. What would you target for this tunnel project? All right. Give it another few minutes to see if you have any answers about how you would allocate your budget. Bet it all on river boreholes, okay? The shafts and one borehole in the river. Holes and pieces on land, geophysics over the water, testing the boreholes in all the units. Go back to the client and ask for more money. Geophysics along the river, borings outside. 3 drill holes at each shaft, 1 in the middle, 2 holes, 1 on each side, a few lab tests. See some prioritization of testing and clay clogging. So I like the variability of the answers that we're getting here, and I think again it comes down to the answer is it depends. It depends on risk tolerance. It depends on key information. Do you have any project information from other projects nearby? But I like that everyone's targeting the shafts. I mean, drilling holes at the shafts is a key thing to do, and making sure we're characterizing each of the geotechnical units. That's great. Don't waste money on geophysics. I see we have some fans of geophysics and some not fans of geophysics, and I think that's pretty true to industry. So thank you for all your answers there. So then I'm going to move on to the last part of the presentation, which is about data interpretation and visualization. So once we've collected all this information, I mean, part of it comes down to writing our reports and our deliverables and putting together our geotechnical baselines. But again, I'm not going to talk about those in a lot of detail today. But one of the things we do is trying to visualize our data. And that can come down to things like fence diagrams and geological profiles. But what's becoming more and more common these days is 3D modeling. So I'm just going to switch screens here and show you some examples of 3D modeling of geotechnical site investigation information. So this first example here is using, and I'm hoping this plays. Oh. So this is an example of a project that displays in 3D both the existing site investigation information and uses the interpretation of that information to help with planning new borehole locations. So the options you see in red there are planned boreholes, and everything you see in black that has colors are existing boreholes. So as we zoom in here, you'll see the different stratigraphic units in the boreholes and the interpreted geology. And these dark gray lines are expected shear zones or dips, and we're targeting those, and we're able to select locations to plan our site investigation holes by using this 3D model. It helps facilitate ensuring we hit those units. So I have one more example here, and this is a much larger project with a significantly more site investigation. There's many boreholes here, and you can see how the boreholes were used to develop this 3D model, and then the 3D model itself can be used to export both long and cross sections of the tunnels. So this is using Leapfrog, which many people on this call are probably familiar with. But you can see the export of the 3D model into 2D for communication purposes. Great. So as we said at the beginning, your site investigation really comes down to mitigating your risk, and uncertainty is the major driver of your site investigation program. That comes down to the inherent in situ variability that we deal with in tunneling projects. So the fact that geological materials have been worked and reworked over time, as you can see on this top right geological model, very, very complex conditions, and that the conditions are going to vary across our project area. So we need to know what we're going to encounter during the tunneling excavation. And there really comes down to how much uncertainty is acceptable. Do we have an adequate amount of site investigation? Can we rely on the lab testing data that we have? We talked a little bit about the variability in lab testing and whether that's reliable or not, or if that's actually inherent variability within the rock mass condition. So in summary, site investigation programs are really used to reduce that uncertainty and to allow us to have more accurate cost estimates and schedules. We know from project after project after project that unforeseen ground conditions can have a huge impact, both time and money. So whatever we can do to reduce the risk of unforeseen ground conditions is of value to the project. So the extent of your site investigation program should really consider the complexity and uncertainty of your geology, what existing geotechnical and geological data is available from past projects, where your project is located and the accessibility of your site, whether you're in an urban area or a really remote area, what the depth of the tunnel is and the alignment, what available funding you have, both for the site investigation program, but also for risk and for contingency management. What stage of the design are you at? Are you at the beginning? Are you at concept level? Are you at the end of detailed design? What's the timeline of the project going forward? What are the accuracy requirements of your schedule and your cost estimate? And what is the tolerance for risk? So with that, I've reached the end of my presentation. I noticed that I missed a couple questions in the chat, so I'm just going to go to those now. So there's a question about what are some effective ways to measure in situ stress if you don't have information from similar projects nearby. So the different types of in situ stress measurement vary depending on your ground conditions. There's overcoring, which is a method of in situ stress testing, which is appropriate for hard rock. There's pressure meter testing, which can be pre-bore or direct bore pressure meter testing, which can be appropriate in some soil and rock conditions. So there's different methods. As I've said before, the answer is it depends what's appropriate. And the challenges with in situ testing is you don't always get good results. Usually you'll get some results, but the appropriateness of them for using in situ stress estimating varies. And then I see another question from Sam about where is table 4-1 from? Guidelines for accessing exploration needs for tunnels in rock. So Sam, I'll get back to you with the reference for that table. I believe it's in the presentation, but I'll get back to you. Any more questions? How do you effectively advocate for additional site investigation if the client is not willing to spend enough? Ooh, that's a good question. So I think it's a balance of showing them what the upfront investment in site event investigation provides versus the risk you're mitigating. So there's those tables we can use for reference that show where you fall in the band and the amount of claims, but it really comes down to what is the risk for the client. So if you don't do that site investigation, what is the potential outfall during construction? Is it that there'll be a massive claim? Is it that the appropriate construction method won't be selected? And what is the cost or schedule repercussion of that? Do you have any more questions?
Danny, I don't know if there's any more questions coming in, so but that was a fantastic presentation. Thank you, thank you. The interaction in your presentation was super cool, and that was like a lot of fun to be a part of. But I think we might as well leave it there. We're about, I guess, like 10 to 4 here in the Eastern time zone, and so if anybody has any questions that they're thinking of or thinks of questions after the fact, please email them to tac-ym@tunnelcanada.ca, and we will forward them on to Danny for you. So I think that's it. That was great. Thank you.
Thanks, everyone.
Thank you.
Bye.